Okay, 111 students, I thought I'd run through the exam with a little video for you. This will kind of give you a chance to, number one, kind of self-grade. You already know your score on the multiple choice, but also on the free response, it'll give you some kind of idea of how you did. And so it'll take me a little while to grade them. And so you might be curious how you did. So that's the one purpose of this little video. And the second is the other half that, okay, what did you do wrong or what did you do right? And so particularly if you did it wrong, it's a chance to kind of recognize what you did wrong and learn from that mistake so you don't make it again and you do that much better the next time. And so that's why I think these videos can be helpful. So hopefully you have enough time to go through this, or at least kind of look at the ones that you think you have a chance to do some learning from. So let's go through the 10 multiple choice questions first here. It says, how many electrons must be removed from a neutral object to leave a net charge of... And so a neutral object, I think as you know, is made out of an equal number of positives and negatives. And so how many electrons? So if we move electrons, we're moving negative. That means the net left over will be positive. Okay, so there is a positive. And every time we remove one, and this is kind of the key to the problem, is that this is the amount of charge, 1.602 times 10 to the 19 coulombs for each electron. So if you removed one electron, that would be the charge Q. And if you moved 2, you would multiply it by 2. 3, you'd multiply by 3. And if you moved n electrons, you would then get that much charge. And so that much charge is 2.254. And then don't forget the microcoulombs, equaling 1.602 times 10 to the 19 coulombs, then equals n. So we can get how many electrons by a little division here. So 0.254 times 10 to the minus 6 divided by 1.602 times 10 to the negative... Oh, I must have hit something wrong here. Try that again. 0.254 times 10 to the negative 6 divided by 1.602 times 10 to, oh, maybe that's where I hit it, enter there, times 10 to the negative 19. All right, and so we're looking at about a 1.59 times 10 to the 12. Well, 59, 10 to the 12. Looks like the third one down, which would be option C while you're doing the multiple choice. All right, so let's go on to the next one here. The next one says, find the magnitude of the net electric field at point A. The two particles in the diagram each have a charge. Okay, the distance separating them is, okay. Point B is halfway between them. Okay, so halfway between them would be 3. And then the distance down here would be 4. And that's a 3, 4, 5 right triangle. So this is 5. Although if you don't remember that, you can go 3 squared times 4 squared is equal to the hypotenuse squared. And so 9 plus 16 is 25. Square root of that is 5. So there's the distance away, 5. And we would then have some kind of an electric field pointing this way. And the other one would have identical. And that's important here because what that would tell me is the x components cancel. And so the electric field in the x direction is 0. And the electric field in the y direction would just be twice the electric field of one direction, or of one of them. Okay, so I guess it would look something like this, 2 times. And the electric field from one of them is Coulomb's constant times Q over R squared. That's why that distance of 5 was useful. And then depends what angle. Why don't I do this angle? Then it would be cosine of that angle. Which I could probably save myself a little trigonometry if I just remember that cosine of an angle is the adjacent, the 4, over the hypotenuse. I suppose we could, you know, do like an inverse function of 3 over 4, inverse of tangent, get the angle, and then cosine of angle. But that seems like an unnecessarily lot of work. All right, so 9 times 10 to the 9th times the charge, 7.89 nanocoulombs, divided by 0.05 squared. Then why don't I go the times 2, then the times 4, then the divide by 5. So 1, 2, 3, 4. So it looks like about a 4.5 times 10 to the 4. So again, third one down. Okay, good. And you can see both of those were right out of 18. Let's see. Some filters use an electric field to remove small particles from the air. The system charges the particles passes through parallel plate. Inside the filter, a positive charge, has a mass, a charge, and an electric field. What is the acceleration of the particle? So acceleration is force divided by mass, and again, right out of chapter 18, charge times the electric field is the force, and then just divide by mass. So this one's a little more straightforward. The second one here was a little long. This one was not too long. But now we've got a pretty straightforward one. We're just going to take the charge, 1.9 times 10 to the minus 6 microcoulombs, times an electric field of 6.25 times 10 to the 6th. So there's the charge, there's the electric field. And then I'll divide by the mass, 5.65 times 10 to the negative 12. And looks like about a 2.10 times 10 to the 12. And we're looking at another C again. Okay. Onto our little bit of circuits here. Here we said that you could think of capacitors as one when you combine them. And so I think the first step maybe is to kind of recognize that 1 and 2 are in parallel. And so maybe I'll think about these 3 as these 2, where I combine 1 and 2 together. And since they're parallel, you just add them together. So 24.5 added to 6.58, and looks like this is about a 31.01, and then I'll just put 13.7 here for number 3. And I should watch my units. They're all nanofarads, so okay. Now I'll recognize that those 2 are in series, and so now I'll get an equivalent of all 3 of those. And this is where the reciprocals of these add up to the reciprocal of this one. And so I like to say, okay, I'll take the reciprocal of the first one, add it to 13.7 reciprocal, and if I hit enter, that is the reciprocal of the equivalent. So let me take then the reciprocal of that to see what that equivalence is. And we're looking at about a 9.51 nanofarad. So 9.51 nanofarads would be B here. All right, a cauterizer uses an electrical device to stop the bleeding during surgery. A typical cauterizer outputs, so here's the current, here's the voltage. What is the resistance? So this is a straightforward Ohm's law. They give you the current and voltage and ask for resistance. So let me write resistance as voltage divided by current. And so now I can take the voltage, 15.5, and I'll be careful with my units, kilo, so that's 1,000 volts, divided by 2.3, and then milli, that's 10 to the minus 3. In fact, by the way, you can see the 3 and 10 to the minus 3. This is going to be millions. It'd be like 15 divided by 2 here. So you're looking about 7 million somewhere. So, you know, it's probably B there. 1, 2, 3, 1, 2, 3. Yeah, 6.74. There it is. 6.74 mega ohms. Now, number 6, it looks like we've got a 1,000 watt microwave, and it's plugged into the wall here in North America. That's, I guess we don't really need to know it's North America once we have the voltage, although those go hand in hand. How much current flows? So power, current, and voltage are all related, and kind of like the one before it, questions giving you 2, you find the third, and so again we're given 2, find the third. So here we have 1,000 watts. We're looking for the current, and we're plugged into 120 volts. So mathematically this would be 1,000 divided by 120. Which makes about 8.33, and I guess we should keep in mind that it's an amp times a volt is a watt, and so power was in watts and voltage, so this is going to come out into amps. So this should be B, 8.33 amps. All right, well, let's keep going here to number 7. Number 7 says, below is a diagram showing a node. Now, this is a more complicated node than anything we directly did in class. I think some of the more node ones are coming up in the free response somewhere in here. I think we have a circuit that, yeah, I think it's this one here coming up. Yeah, so we have like a node A, and it kind of veers in 2 directions. But the point is, what comes in equals what goes out. And so here we have 6 in/out. And so let me look at the ones coming in. So there's a 2 coming in. There's a 4 coming in. Okay, and then that's all we have going in. Coming out is a 3 from number 2, a 3 from number 5, and a 1 from number 4. And so what we have so far is a list of 7 coming out and 6 going in. So to make that balance, we must be going in, and it must be a 1. So there must be like a plus 1 here. 1 going in. So these things that say out, I can eliminate. Coming in would be, I guess, right there. So A, 1 amp flowing inward. All right. On to number 8 here. Ooh, a little bit of calculus on this one. So this might be a hard one. It says, which of the integrals, now, here's a good idea. We don't have to actually do the integral, is needed in order to solve for the charge as a function of time on a discharging capacitor. Well, I'm not so sure you have to redraw the circuit like I'm about to do. But like I said, I want to use this as an explanation here. But we did this in the lecture in the notes. And you could, look at your notes. I think we're going to end up coming up with this one if I remember the lecture right. But let me not assume anything. Let me just go around and apply a Kirchhoff's around the loop. And so as I start here, there would be a change in voltage, which we would do Q over C. And then as we go around the loop, there would be a decrease. So if the current is going this way, there's a discharge. And then that would finish the loop. Okay. And of course, what makes it a calculus problem is remembering that the current is really how the charge changes with time. And so now we have an equation that has charge, it has capacitance, has resistance, and it has time. And we'd like to get time by itself because that is the question, you know, what is the amount of time? So again, like I said, probably don't need to do this much math to answer this problem. You could have kind of started right here. And if you remember, we kind of did this. We put all the time variables on one side and all the Q variables, the charge, on the other side. And I think when we did it, we put the R and the C, which are, you know, constants. They're not part of the varying part of this problem. The varying part of this problem is as time goes on, so time varies, the charge decays. So our two things that are changing, our variables, is Q and T. So R and C are certainly part of the problem. And then we did an integral here, but maybe just to make it kind of look like what we want, we should get time by itself. Because then, and these are just constants, so you can pull them out and put them out here on top. And then this would be then what we mean by a delta t. So if we get dt by itself, the integral is dt. That's kind of the crutch of the problem here, to be honest, is to write off Kirchhoff's law and get dt by itself and do an integral. And the stuff on the other side would give you the dt. Whether it's an easier integral to do or not doesn't really matter because we have right here as our answer. Oh, and shoot, forgive me, I got a little careless. I didn't include a negative sign. Yep, my bad. The Q here is the Q through the resistor, and this is the Q on the capacitor. And what goes through the resistor is what comes off of the capacitor. So if I let Q represent the charge on the capacitor, and I change this Q that goes through the resistor to a Q that comes off of the capacitor, I have to say, well, it's a negative of that, because what comes off the capacitor goes into the resistor. So what one loses, the other one gains. And so there really should have been a negative sign in there. And so I apologize for my carelessness on there, but it didn't really kind of stop me from recognizing, other than I saw that negative in there. Anyways, that, I guess, would make C as the answer to that hard one. Some magnetism stuff here. All right, so it looks like these last two, not a surprise, are left to magnetism, but here's a battery, and we're going to run some current. It's positive, and you can see how it's wound up, and so the little blue lines represent the current going around here. And if you remember what we called a right-hand rule here, is we can get the direction of the magnetic field from a solenoid here. So I take my right hand and I kind of curl my fingers like the current is curling. My thumb would give me the field. And for whatever reason, I'd like to use the green marker, or pin in this case, as the direction of the field. And so one of the things I kind of see here right away is, as I have this coil, this solenoid, the field is going from the right to the left. And so it's not to the right, it's not out of the screen, it's not to the right, it's not out of the screen, it's to the left. And I guess that alone kind of narrows it down to just kind of two options here. And then now we've got a calculation to do. The magnetic field is the mu naught times N over I, where the N is what we call the turn concentration, or really the turn density. And so this would be the number of turns divided by the length of the solenoid. So putting in my numbers here, mu naught, the permeability of free space, is 4 pi times 10 to the negative 7. The number of turns, I said the solenoid has 75 turns. Maybe I'll do then the divide. It has a length, and just let me make sure I watch my units here. Instead of 9.25 centimeters, let me do 0.0925 meters. And then finally the current, which is 2.18 amps. And so if all that comes out well, I'm looking at 2.22 times 10 to the minus 3. And 10 to the minus 3 is milli. So 2.2 milliteslas to the left should be the correct answer then for the solenoid. All right, and then finally the last of the multiple choice, and then on to the harder, more time-consuming ones here, is, and that picture didn't print. Oh, yeah, it printed. Okay, good. Good. This then would be this charge, if you will, and it's moving in a magnetic field. So the charge of this much is moving upward with a speed of this much in a magnetic field of this much, as shown in the figure. Determine the initial deflection, that is both the magnitude and the direction of the charged particle. Okay, so the force on a moving charged particle is given by this fancy equation where we can calculate the number and we can also calculate the direction. And the direction we get from that right-hand rule number 1 here. Okay, and so right-hand rule number 1 is where we do any type of cross product. We did that quite a bit actually in Physics 110. But you take your right hand and you put your thumb in the direction of the first one, which in this case is the velocity, and you put your fingers in the direction of the magnetic field. And so I guess for me it would look something like this. I'd kind of have a 45-degree angle between the thumb, the velocity, and my my thumb, velocity here. Okay, like this way. So my thumb is the velocity, and my fingers are the field, and then my palm is going to give me the direction of the force, which in this case then would be into the screen here. And so let's see, this one has an into the screen, and this one has an into the screen. All right, so I guess from direction alone, I'm down to 2. And then we got the numbers. And so the numbers calculate this way, Q, V, B. And then don't forget that the meaning of this cross product is that it's the sine of the angle between them. And so this shows up because of that symbol, the cross product. And in our case is 45 degrees. And so the Q is the 2.54 times 10 to the minus 9. The V, 226 meters per second. The magnetic field, 1.35. And then finally sine of 45. And I better be careful. Am I in degrees? I am, okay. And 45 degrees. Okay, and then I'll hit enter. And if I hit enter on this, 5 point... One, three, five. 45. Well, this is the closest one, but it's not an exact match. Let me check that one and adjust it. But I'm going here with this second to last one. Yeah, a little bothered here by that one. In either case, let me move on here to this next one here, where now we've got some significant work to do. We got a bunch of charges. It starts off by saying this is a quadrupole, and what a quadrupole is, it says how they, you have a positive and negative for the dipole, and when you put the two positives together, here you get double the charge. Okay. It says that the small charge Q, right here, is directly below the 2Q, and Q equals this much. D equals, let's see, D here equals 1.25 centimeters. And then the distance from Q to Q down to the little q is 3.75. What is the magnitude and the direction of the electrical force? All right, well, I'm going to take an advantage of an equation we used a little earlier. I guess we did that during the multiple choice where we had that little parallel plate charge that was asked for the acceleration. And this will be my last calculation. In other words, if I can find the electric field at this point Q from these other three, I then can just multiply by the small q to get the total force. So for starters, I'm just going to do that. I'm going to say, okay, so the electric field for this negative one would be pointing up this way. And this negative one would be pointing over here like this. And the 2q would be pointing something like that. And like we did on the multiple choice, although this one is significantly harder than the multiple choice one, we can see that the negatives, the left and right component, that is the x components, are going to cancel off. And so if we recognize that, we can save ourselves a lot of work here. Okay? And we don't have to do that. Plus, the result of the y would be just twice one of those. So in other words, let's just put these two together first. And so I'm going to say I'm putting the negative q's together. And I'm claiming that the electric field, and it would be in the y direction, is twice the y direction of just one of them. And so, like I said, just one of them would be something like this. And if I call this angle then theta, I would have 2 times, and then I would have Coulomb constant times the q over r squared, and then I would have cosine theta. And here's where I'm going to have to do a little bit of work, because I need to find out what r squared is. And to do that, I need the dimensions. And so maybe I'll draw myself a little picture right here. Here they said D was, and I'll do centimeters here, 1.25. And they said the distance from 2Q is 3.75. And so if this is r, we then say that r squared is 1.25 squared plus 3.75 squared. Okay. So 1.25 squared added to 3.75 squared gives me r squared. So r squared is 15.625. Okay. I guess I'll take the square root. Might make things a little bit easier to think about here. Square roots of r. And so we're looking at 3.95 centimeters. All right. So putting in my numbers, I get 2 times 9 times 10 to the 9th. I get a Q of 2.38 nanu. And then my R, and got to remember that I was doing everything here in centimeters, but this Coulomb constant is in newtons and in meters. So before I put it into the main equation, I'm going to convert my centimeters into meters. And then also this cosine, and then here again where I have a little bit of work, I'm calling that the angle theta. That's the angle that goes right here. And so maybe I'll just notice that tangent theta is 1.25 divided by 3.75. Okay, so 1.25 divided by 3.75, and I'll take the inverse tangent of that. And so this is 18.4. Okay, so 18.4 degrees here. All right, so now I get a number for, I think, those two here. And see what I get here. 2 times 9 times 10 to the 9th times 2.38 times 10 to the negative 9 divided by 0.0395 squared, and then times cosine of 18.4. All right, so we're looking at 26,053 newtons per coulomb. And that's just these first two, which are negative, and so the field points towards them. And like I said, this is the y component doubled. So this is the upward y component for those two. Why don't I then kind of do that same logic and say, all right, so this is from the Q's. What would be the field from the 2Q? Now, fortunately for that one, this point is straight down. So there's not going to be any kind of sine or cosine. And I'm not combining anything together. So this is just K times 2Q over R squared. Where the K is Coulomb's constant, 9 times 10 to the 9th, times 2. And again, the Q is the 2.38 nanocoulombs. And the R is just this straightforward distance. So we don't have any, Pythagorean theorem or anything fancy. So 0.0375 squared. All right. So 9 exponent 9 times a 2 times a 2.38 times 10 to the negative 9 divided by 0.0375 squared. Enter. And so this is 30,464 newtons per coulomb. Okay, so finally then, I'll call it E total. Would have this much down, and so that means I got to subtract that much because it's up. So 30,464 minus 26,053. So maybe I'll just take the answer that's already there and say minus 26,053. And so we're looking at about 4,411 newtons per coulomb. And that's the real hard part of this problem, because you got to give an angle, you got to put the two together. You can save yourself a lot of time if you notice that the x and y's cancel for these two. You have to also notice that they're going to be battling each other. That is the field from the negatives and the positives. But then ultimately we get to the last step and the easiest step. And the force then is just the charge you're going to place there times the field that exists there from the other charges. So we're putting a small 0.23 times 10 to the minus 9 coulombs, that's that little q, at a spot where the field is straight down with a value of 4,411. And so now we just multiply. So I'll take that number and go times 0.23 nano. And come up with a force of 1.01 times 10 to the minus 6 newtons. Yay! And so that was a pretty hard one. I hope you did well on it, but that had a lot of pieces. But in summary, let me say it again. You're just trying to find the electric field first, and so it would be the electric field from the other ones. And so even though there's 4 charges on here, I'm not going to pay any attention to the little q till the end. I just want to know what the field is from the other 3. And then the 2 of them I would do first because they are, there's something nice about them. The x goes away. The y is just double one of them. So you only have to get the y component of one of them and then double it. And then you realize that the y component is the same as the direction as the other one, or opposite actually. But you don't have to do any like tangents or sines or cosines. Makes it kind of nice. And then you get your answer. So hopefully you recognized all those patterns, those symmetries, because otherwise you would get overwhelmed with the work and you would think there's just not enough time to complete this one. And therefore not enough time to complete the whole exam. So take advantage of those symmetries. All right, so let's go on to B here. So B says, let's consider this circuit over here. So we've got one power supply, comes along, goes through resistor 1, looks like it branches off and goes through a 2 and a 3, regroups and comes back. Okay. I'll write down the Kirchhoff's node and the loop equations for this circuit diagram. Now, ultimately, B says calculate the currents in it. And I debated on just writing that out and say, hey, just calculate the current. But it is kind of nice to kind of help you through this. And that's kind of what A is. And so let's go ahead and look at, say, our nodes, A. So current 1 comes in and 2 and 3 go out. So I guess it would look like this. Current 1 coming in equals current 2 and current 3 coming out. And B isn't really much different because as you watch this, although you do have to recognize that it would still be current 2 when it comes around here and rejoins with this 3. So current 2 plus current 3 coming in has to equal what comes out, which would be right here. And if you follow it around, it's got to be that number, so it would be number 1. And so there would be your nodes. Now, if you do a loop, the loop rule is adding up the voltages. And so if I do my left loop, and maybe I start right here, and it doesn't really matter what direction you go, but I'll just go the standard clockwise. I go from here to here would be plus 4.5. And then since I go with the current, this would then be a minus 212I1. And then you would come down here and go minus 105 I3. Okay. That would complete the loop, and we'd get back where we started, so it's equal to 0. Now, the right-hand loop, and maybe I'll just kind of start in the bottom left corner here and just go around. But as I go from A to B, it would be an increase in voltage because I go against the current. The resistance would be 105, and we're looking at current number 3. But then as I come up to A and hang a right here, I would have a flow with the current. So there's the minus, and the resistance is the 275. And I2, and that would give me a 0. Now, if you do the big loop, you might remember my kind of warnings from the lecture. Mathematically, it doesn't give you anything new. In other words, the left and right really add up to that. So suppose mathematically you could just add these two lines together. And in fact, if you did, you could kind of see how this 105 I3 and this 105 I3, this one being negative and this one positive, would be going away, and you would just have these three terms. And that's exactly what I'm going to get if I go around. Starting here with the big loop, I will go plus 4.5 minus, because I'm going with current number 1, 212 I1. Going with the current for number 2, so it's a minus 275 I2. Comes around and completes the big loop. So obviously you can see, just add those two together. Kind of like B is the rejoining of the currents after they separated. So, that's not a new piece of information. And so, of course, when we go on to part B here, where it says calculate these currents, we've got 3 currents. We've got 3 unknowns. And so that's kind of perfect here because, I can use this equation here, and, B is just the repeat of that. And I can use these 2 equations because, again, outside is just the repeat of those 2. But I have my 3 equations, 3 unknowns. And that's one of the things that I hopefully you remember from your math class. If you have an equation with 1 unknown, you can solve it. But if you have 1 equation and 2 unknowns, you can't solve it. There's not a unique solution. And then on the other hand, if you had the 2 equations and 2 unknowns, then it is unique again. So you can solve it. And then likewise for 3. And so if you have 3 unknowns, you have to have 3 equations. You can't solve a unique answer with only 2 equations. But I have my 3 of this one, and that one. And then this will allow me to get the currents. Now, to do that, I might need some paper beyond here. So let me grab my yellow pad here and kind of put these equations. Why don't the first thing I do is put equation, this first one, I'll call this the node equation, or number 1. And so it says I1 equals. So everywhere down here where I have an I1 in these 2, let me get rid of it. So this left-hand one would be 4.5 minus 2.2, I'm sorry, 212 times current number 1, which I'll write as I2 plus I3. Okay. And then minus 105 I3, and that equals 0. Now, the second loop one doesn't have an I1. Okay. So if I pause for a moment and realize I've taken this one here, the first node one and the first loop one, and put them together, I have eliminated I1 completely, right? There's only I2 and I3. And if I think about this as an equation together with this bottom one that I haven't used yet, or the right loop, that has a 2 and a 3, and this has a 2 and a 3. So now I've gotten what I've wanted, which now I'm down to 2 equations, 2 unknowns. Now maybe I'll simplify this a little bit. Why don't I go 4.5 minus, and I'll do a distributive. So 212I2. And this would be an I3 with that I3. So that's 317, I believe. Let's just double check that. 317. And this would be a minus and a minus. I3 equals 0. Okay. So again, this one is just a simplification of that one. And that one is combining the first two. Okay. Now, let's think now that I have this one, which has 2 unknowns, and this one I haven't used yet, has 2 unknowns. Why don't we say solve this one for I3? And so maybe I'll just do that right here. I3. See, I would do that by moving the 275I2 to the other side of the equation, and then I would divide by my 105. Okay, so that's going to give me 275 divided by 105, and I'm going to get 2.619I2. So that's kind of this bottom equation simplified to an I3, because I can put that into here. So this would be 4.5 minus 212I2 minus 317, and then I3 is 2.619I2 equals 0. Nice. Because you can kind of see here that if I take this number and then multiply it by the 317, all of this is 813. Now, technically negative. But I'll have another negative to go with it, because that is also now an I2. So I've got an I2 and an I2. Basically, I've now substituted out 2 of my variables. To get here, I substituted an I1, and then from here to here, I substituted I3. So I got the I1 from here and the I3 from there and put them into this equation. So I guess I'm using this one as my master equation, if you will. Solving this for I1, solving this for I3, and putting them into here. But into the story is I have just an I2, which, whoops, that should be a negative, which makes this very solvable. I'll imagine moving this to the other side. That's what would make it would be positive, and I would just have a 4.5 on that side. So then I would divide it by that last answer. So 0.00432, or 4.32 milliamps for number 2. So number 2 right here is 4.32 milliamps. All right. Well, once I have that one, let me come back to maybe this would be the easiest equation. There's all kinds of ones, but this one gives me I3 directly from I2. In fact, I'll just do that one. So if I have my I2, and I multiply it by 2.619, I get my I3. So my I3 So what I get there, I'll do it in milli. So this would be 11.3. If I move the decimal 3. So here's 11.3 milliamps. Actually, maybe I'll go 3.1. How about that? And then, of course, remembering that number 1 is the sum of these two. So if I just add them, let's see, that's a 3, that's a 6, that's a 5, and a 1. All right, so I number 1 must be 15.63 milliamps. Nice. So again, not really an easy one, but 3 equations, 3 unknowns. Hopefully you did a good job writing down the equations and then the math. And by the way, you could use that technique that I showed you how to do the linear functions and the matrices on your calculator if you want. So whichever method you want. And there's other methods. I did the straight what they call the substitution method, but there's elimination, there's Cramer's rule, there's using your linear algebra in your calculator. So whichever method you want. But hopefully they all come out to be this answer. And just kind of as a check, remember this math says that these two should add up to give me that one. That's what A and B is. And of course they do. Those two do add up to there. It might be nice also to kind of go, around this loop. This is, an increase of 4.5. So if you go from the voltage of number 1 and number 3, they should add up to this 4.5. So it might be kind of nice to go 2.2 times current number 1, which would be 0.01563, and recognize that this would be about a 3.31 volt change here. And then this should be 105 times the current in number 3, which is the 0.01131. And so this should be about a 1.19. So I go up 4.5. I should also go down 4.5. That's where this left loop is. And so let's see, this would be a 4.4.5. Yeah, so that works. And of course, this other loop said that this increase of 1.19 should be the same as that decrease going around this loop. So this voltage here should be 1.19. So let's see what I get after I got my answers now. And so current number 2 is 0.0432. Oh, it should be an extra 0 there. 275 times 0.00432. And that should be about a 1.19. Yeah, 1.19. Good. See? So sure enough, around that loop. And then around that loop, it's also 0. All right, so they check out. So one thing I know about these current ones, if you have time during the test, you can do what I'm doing and double check everything. And you'll end up knowing that, hey, I did get it right, or no, I didn't get it right, because the voltages check out and the currents check out. All right, finally on to this last one here. It's a magnetic one here. Here it says a wire is put between two magnets. Now let me pause here as I look at the magnets. Again, I always like to do the magnetic field in green. And so we're looking at a field that goes from the north to the south. And that's not in the diagram, and I think that's going to be important here. So that's why I just wanted to pause and draw it, because when I read that, that was the first thing that went off in my head, that I go, okay, wait, where's the field in this one? And it wasn't in the drawing, so I had to take a mental picture of it. And you don't have to draw it in your drawing, but I hope first thing you did is what I just did, is you mentally said, okay, there is a field here from north to south. Okay, so a wire is put between two magnets. The wire carries a current of, and so they give us the current in milliamps, and is in the direction shown. So we know the direction of the current. The magnitude of the magnetic force. So they give us the magnitude of the force, but of course not its direction. The section of the wire between the two magnets is also 15 centimeters long. And so between the two magnets, we're looking at a distance of 0.15 meters. All right. What is the magnitude of the magnetic field at this location of the wire? Well, maybe I'll put it up here, but another nice cross product one we learned was, whoops, almost wrote it backwards, current times the direction of the length or the direction of the current cross B. And so there's that cross product one. Kind of reminds me a little bit of this one. And in fact, these are mathematically connected. In fact, this one was derived from this one because a current really is just a bunch of moving charges. And if you put a bunch of moving charges together, in other words, Q times V does give you the length times the current. The current, the charge and the velocity is the current over some length based on the velocity. So, well, let me not digress. It would be a fun lecture to connect those two together. But I guess we already did that in the lecture part of this class. Now let me use that result here in the exam. Because it's a cross product, I know two things. Direction, which I think they ask later on. So let me hold off on doing right-hand rule here. Let me just do the magnitude. So the magnitude is the current, the length, the magnetic field, and the sine of the angle between them. That's, again, like we did in the multiple choice number 10. And in our case, we know the force. It's 4.15 times 10 to the minus 3 for the millinewtons. We know the current is 785 times 10 to the minus 3 for the current. The length is 0.15 meters. And this is what we're being asked, the field. What is the magnitude of the magnetic field? So B is the unknown. And this is where the picture of the field comes into play. The field going from north to south means that there's a 90-degree angle between the field and the current. And of course, sine of 90 is just 1, so that's going to make it real easy to do on my calculator. All right, so taking this number, 4.15 times 10 to the negative 3 for the force, and dividing it by the current, 785 times 10 to the negative 3, and dividing it by its length, you get a magnetic field of 0.0352 Tesla. So there's the A part of it. Now the B, it says, what direction will the wire move? So this is the direction of the force, and explain. So this is the right-hand rule, and you can even kind of draw a picture here. But again, our right-hand rule says put your thumb in the direction of, in this case, the L, the direction of the current. B will be the fingers. The second one is the fingers here. Again, kind of like we did back here in number 10, where we put our thumb in the direction of V and our fingers in the direction of B, and the force was the direction of our palm. So same thing, direction of our palm. So let's see, I'm going to have to do, let's see, thumb in the direction of the first one, fingers in the direction of the field, and so my palm is towards the screen. And so maybe I'll say out of screen. How about that? And then, well, I guess I verbally explained my reason. So let me not write that down and just call it quits to the video. All right. Well, hope that helped. Hope you did well. Hope you learned a lot from your mistakes. Take care.